Um, well, thanks, Michael, for the very kind remarks. And thanks for the Institute of Physics for selecting me for this honor, as well as for the invitation today. I'm very pleased to be here to have a chance to give this lecture. And I'm also looking forward to changing the page because it contains a small misprint that's been pointed out. Now, what I'll really be explaining in this talk is how, over the last 40 years, string theory has repeatedly forced physicists developing it into directions that they didn't anticipate and frequently didn't want. So, as I've written here, I'll be describing how string theory has grown beyond anything that anyone conceived at any step along the way. And broadly speaking, I'll be talking about 3 episodes. I've tried to distill it into 3 episodes where this has happened. My purpose isn't mainly a historical retrospective. The main point is that, rather, that I believe that this process, in which a theory that physicists have stumbled on but only understand to a limited extent, forces us into directions which we don't anticipate or really fully appreciate going in, is far from finished. And we still can't really conceive of the end of the journey. I'm actually at best only semi-qualified for historical account for at least one obvious reason. And it is simply that there are a lot of the developments I didn't participate in. So a lot of the important stages, which I'll tell you about, are things that happened, in some cases, before I was even a graduate student, but certainly before I was involved in developing the ideas. As a partial excuse, I'll observe that few people have participated in all stages of this process, as by now it's gone on for more than 40 years. In my case, I wasn't directly involved until the early 80s, or if you were generous, a few years earlier. And a lot of things had happened by then. And since I wasn't involved then, I can't say what I'd have thought at the time of the idea of inventing a whole new theory by concocting a scattering amplitude out of whole cloth. So this scattering amplitude was the Veneziano amplitude, and the details of the formula don't matter that much. S and T are basically relativistic versions of energy and scattering angle. And Veneziano guessed a formula that was supposed to be an approximate formula for the scattering of 2 pions, elastic scattering, which had magical properties. It proved to be the starting point of a completely new theory, although that was certainly hard to imagine at the time. I can't say what I'd have thought about it at the time. I can only say that looking at it in hindsight, it seems like an utterly astonishing starting point for getting something significant. This is a rather complicated formula, after all. Gamma is the Euler gamma function, which is, I mean, it's been known for centuries, but it's still a rather esoteric function. And such a complicated formula as on the right-hand side is usually the output of a calculation where you start with some simple equations and solve them and you get a complicated answer. You don't usually guess a complicated answer and get anything useful out of it. So I think it's surprising that that was useful. Now, there's a reason that this formula was invented. It had to do with hadron physics. In other words, the hadrons are the strongly interacting particles, the familiar ones like the proton and neutron, and the slightly less familiar ones like the pion, the kaon, the delta, and so on. So by the time this work was done in 1968, the hadron resonances had proliferated at particle accelerators. And this had actually made some physicists despair of describing the nuclear force, that is, the strong interactions, within the known framework of local quantum field theory. But you can't get anywhere with only a negative assumption that there aren't going to be local fields. You need some kind of positive idea about what there is instead of local fields. And there was a positive idea that led to the Veneziano amplitude. But it's again a rather mysterious idea. The idea was that since there were so many hadron resonances, when you scatter, for example, 2 pions, or for example, a pion and a proton, to mention something which is more practical experimentally, there are many possible resonances contributing to the scattering process, where you create an unstable state and then decays. There were so many resonances that it was at least imaginable that resonance scattering, the creation and decay of resonance, was most, or in the extreme case, all of the scattering amplitude. So the following question was asked: can a scattering amplitude that's given by a sum of resonant contributions only be the whole answer? So again, this is a formula whose details don't matter that much, but A is the scattering amplitude that depends on the energy and the scattering angle. When you have a resonance, you get an energy denominator, like in non-relativistic quantum mechanics, where the scattering amplitude has a pole when the center of mass energy equals the mass of the resonance. And then the numerator is a Legendre polynomial. That's what Pn is in the numerator. But anyway, you can write a formula for scattering due to resonances. And in normal physics, it's important, but it's never the whole story. In fact, with only finitely many resonances, it can't be the whole story, because that would contradict general principles of scattering theory. If you only had finitely many resonances, then the amplitude would actually be a polynomial in T, but it's not a polynomial in S. It has poles. And that would contradict principles of relativistic quantum theory. But experiments showed that there were so many hadron resonances that people imagined there could be infinitely many, which is more or less still the viewpoint today. And with infinitely many resonances, you could at least imagine that resonance scattering might be the whole answer. So again, since I wasn't there, I can't say how well motivated the question was at the time. I'm curious about that, but I really can't judge it. And it's, although certainly I know participants, it's kind of hard to, well, it's hard to know from what people say what I would have thought at the time about how well motivated the question is. However, in hindsight, it certainly proved to be a fruitful one. So, first of all, the answer is yes. I didn't state all the technical details about the question, but properly interpreted, the answer is yes. That's what Veneziano showed with his formula. With infinitely many resonances, resonance scattering can essentially be the whole answer. And the theory that had that property turned out to be much more than just a funny formula that was written down out of thin air. For one thing, it led to a physical picture. Trying to understand that formula led to a physical picture where a meson was understood as a little string with charges at its ends. So in this picture, the meson resonances, which are the poles in Veneziano's formula, are vibrational states of the string. Just like a violin string, this kind of string has got many states of excitation, many states of vibration. For a violin string, those are the fundamental note and the higher overtones, which fit together to give the richness and beauty of music. Here, the many hadron resonances, the many meson resonances, which motivated Veneziano in the first place, were ultimately understood as vibrational states of a string. So that physical picture that I just stated, that a meson is a little string with charges at its end, is now believed to be qualitatively correct as a description of strongly interacting particles. The charges are what we now understand as quarks. Or at least it's qualitatively correct as a description of the mesons. The story is a little bit difficult for the baryons, like the proton. But at least in its simple versions, it's only qualitatively correct. Now, about 5 years after the Veneziano amplitude, a competing theory of the strong interactions emerged, which was far more successful. It overcome many problems that were not tractable from the point of view of the Veneziano amplitude, so much so that for some years string theory went into eclipse. Now, later developments showed that what appeared to be the failure of string theory as a theory of strong interactions wasn't the last word. Ultimately, string theory has taught us a lot about QCD, most recently by shedding light on heavy ion collisions at the RHIC accelerator at Brookhaven, and there's probably a lot more still to come. The modern view is actually that QCD may be equivalent to a not yet discovered string theory. But even though that's true, it's not the main reason that string theory survived. from this period when it appeared to go into eclipse as a theory of strong interactions. The main reason that string theory survived was not that it has some relevance to strong interactions. It's that the idea that led to it was actually wrong for the strong interactions, but it was right for something else. The physicists who started string theory had despaired of the applicability of conventional local field theory to the strong interactions, but they were wrong with that despair. The success of quantum chromodynamics showed that the strong interactions can be described in the then already standard framework of local relativistic field theory. But there's another problem in physics, perhaps a bigger problem, for which this idea is right. That's the problem of quantum gravity. Both gravity and quantum mechanics are part of nature, so there should be some way of making them work together. But the nonlinear structure of Einstein's theory of gravity makes that very difficult. So quantum mechanics and gravity both exist, but it's hard to make sense of quantum gravity by the usual algorithm of quantizing classical fields. Because if you take the classical field to be the gravitational field in the form described by Einstein, you'll find out that you run into a maze of infinities when you try to do the quantization. That's a result of the nonlinear mathematics that Einstein's theory was based on. Now, in the context of gravity, there can't be a gauge-invariant local field phi of x, where phi is the field and x is a space-time point, for a reason that's so basic and elementary that it's actually easy to miss. The reason is that x itself isn't gauge-invariant. Einstein's gauge symmetry, the principle of general covariance, invariance of the theory under diffeomorphisms of spacetime, the gauge symmetry exactly acts on x, and therefore it's impossible for a local field phi that depends on x to be a gauge-invariant concept in general relativity. So a theory of quantum gravity is actually not going to have local fields that are functions of spacetime, as we have in other branches of physics, in electrodynamics or in the strong interactions. This was, as far as I know, first pointed out by Bryce DeWitt in 1968, which coincidentally was the same year that Veneziano wrote down his amplitudes. Though again, as far as I know, it was decades before the two facts were related. In view of Bryce DeWitt's observation, a theory that has gauge-invariant local fields cannot describe quantum gravity. Of course, there's no immediate converse to this statement. Just because you don't have gauge-invariant local fields doesn't mean you're going to have quantum gravity. So the inventors of string theory wanted a theory without gauge-invariant local fields because they mistakenly thought that that's what the hadron resonances were saying. But the fact that they did without gauge-invariant local fields certainly didn't ensure that they were going to get quantum gravity, which in fact they didn't want to get, because that wasn't part of the world of strong interactions. But it's what happened. So from rather early days, it was found that string theory generated massless spin 1 particles from open strings, which had properties, I called them gauge-like properties, properties similar to what we have in the standard model of particle physics, and that for closed strings, it generated massless spin 2 particles with graviton-like properties. This was considered bad. Well, the graviton-like aspect wasn't completely formulated in the days when this was considered bad, but it was considered bad because string theory was seen as a theory of mesons and their scattering, and in the strongly interacting world, there aren't any massless spin 1 or spin 2 particles. So, since the theory was supposed to describe the strong interactions in which all the particles are massive, the fact that calculations forced massless particles of spin 1 and spin 2 into the theory seemed like a drawback. So people tried hard to get rid of these massless particles. Dozens or perhaps hundreds of papers were written trying to get rid of them, and that effort failed. That's how we developed eventually confidence that they really are a part of the theory. People who didn't want them tried very hard to get rid of them and failed. But eventually, in the mid-70s, some physicists became daring enough to propose that string theory had been misinterpreted, that the strings were much smaller than had been assumed, not just a little bit, but many, many orders of magnitude smaller, and that the theory should be used to describe quantum gravity and other fundamental forces. Again, I'm only giving a second-hand summary since all this happened before I was in the field. So, and not for the first or last time, the theory veered in a direction that wasn't foreseen by those who had gotten the ball rolling. Now, there actually is a simple picture that helps explain why string theory has a mind of its own. It has to do with what happens to Feynman diagrams in going to string theory. Feynman diagrams are the pictures of space-time processes that Feynman used to describe elementary interactions, originally of photons and electrons, in quantum electrodynamics. So textbooks will tell you how to technically get a number out of a Feynman diagram by a calculation in momentum space. But Feynman actually visualized it more intuitively as a space-time history. Here, space runs from left to right, and time runs vertically. A line here is an orbit in space-time that represents the trajectory of a point particle. So at each time, the particle is somewhere. Later on, it's somewhere else. Classically, the particle would travel, if it's a free particle, in a straight line according to Newton's laws. But quantum mechanically, according to Feynman, we have to sum over all possible histories. A completely generic history would be too messy to illustrate, but the fact that the lines are all in that picture are slightly wiggly just gives us a hint of quantum mechanical fluctuations. Then, according to Feynman, there are space-time events that here are labeled x, y, z, and w, where one particle breaks into two, or two recombine into one. And in this example, I've shown two particles coming into the past. They interact in a certain way. It's called a one-loop diagram. And two go back out in the future. So assuming the particles are all of the same kind, I haven't labeled the diagram in enough detail to make clear if that's true or not. The diagram on the left is a Feynman diagram that contributes to elastic scattering. Just the same process that Veneziano had been trying to describe when he introduced his famous amplitude. On the right, I've indicated the corresponding picture in string theory. So for definiteness, I've indicated a closed string. So at a given point in time, instead of a particle at a definite space, a point in space, there's a loop. Again, these loops are undergoing all kinds of quantum fluctuations, although I've drawn a relatively regular picture so that we can see it. But at one moment in time, the loop is here. At a later moment in time, it's here. The loops branch out and recombine just like the particles do. But there's a fundamental difference. You see, here's the string picture. And it has the property that what's called the world sheet of the string, which I've drawn here, mathematically, it's a completely smooth two-dimensional surface. So any small piece of this picture looks like any other small piece. If you look at the whole picture, you can see that globally, two strings came out in the past, branched and rejoined and went out into the future, so that some kind of interaction happens. But if you look at any small piece, it looks like any other small piece, and locally you can't say whether any branching or rejoining was happening. By contrast, in the traditional Feynman picture, there are definite space-time events labeled x, y, z, and w, where something definitely happened. If you draw a little circle around this point, it looks different from a little circle around a point where there wasn't a branching event. So those branching events are called the Feynman vertices, and those are the space-time moments where something actually happens in conventional quantum field theory. While when we go to string theory, there's no definite space-time moment at which anything happens. Globally, something happens, but you can't make any sense of the question of when and where anything happens. So this has a lot of consequences, of which I'll give you a first list of three. The first is that the infinities of Feynman diagrams disappear. So Feynman diagrams undergo infinities which arise when these distinguished space-time events coincide. So for quantum electrodynamics, Feynman, Schwinger, Tominaga, and Dyson, and so on, showed how to overcome the infinities by a process of renormalization. One always wondered if one could get rid of the infinities a priori instead of renormalizing them away. But anyway, pragmatically, renormalizing them away gave a theory that worked well. It made sense and agreed with experiment. But it didn't work for gravity. If you take the Feynman vertices of general relativity, you find that the infinities that arise when x, y, z, and w coincide are not renormalizable. They can't be removed by the procedure of Feynman and his contemporaries. So the first good thing that happens in going to string theory is that because we've got rid of x, y, z, and w, we get rid of the infinities that arise when they coincide. So the infinities of Feynman diagrams disappear, and whatever it's going to be, the theory is not just renormalizable, but actually finite. The second important fact is that what the interactions are is not up to us. They're fixed once we pick the string. In other words, in this picture, well, in quantum field theory, you first pick the particles. For example, Feynman had electrons and photons, since he was doing quantum electrodynamics. Then we pick a Lagrangian, which determines the interaction vertices. So Feynman had a particular vertex, but if he believed that the electron had had a different magnetic moment, he would have used a more complicated vertex. Specifying the vertex as well as the particles is what it takes in this language to describe what the theory is. But for the string, since there's no vertex, once we know the law of what the string is, what a little piece in the picture means, the interactions are determined. The interactions occur globally when we put together a lot of little pieces which under the microscope look like they just describe locally propagation of a single string. So once we know what the string is, the interactions are up to us. We don't get to decide what they will be. So that's on my initial list of 3 consequences of that picture. The second one is that we don't get to pick the interactions. Once we've picked the string, the interactions are fixed. And the third point is that there's no definite notion of a space-time event. Well, what I'm telling you is really the beginning of that fact. So the prototype of a space-time event in the conventional picture is the interaction event of elementary particles. And that disappears when we go to the string picture. And that's a first hint of what turns out to be the situation, that in conventional quantum field theory, you can make sense of a point in space-time, a space-time event in Einstein's sense. But in string theory, when you look closely, that concept isn't really there. So the last statement means what I've given you is only a hint of this fact, but deeper investigations from this starting point show that somehow the notion of what space and time is at short distances is quite different in string theory from what it is in familiar physics. So physicists, without originally having any intention of trying to get there, arrived at a theory that, first of all, is completely finite since the interaction vertices are missing. Secondly, it's got a massless spin 2 particle since no one could quantize the string without getting one, even though they wanted to and tried hard. And 3, has its own mind concerning what the interactions will be. And the interactions turned out to be, the interactions the theory chooses, are those of general relativity, plus corrections at short distances that are irrelevant for astronomy and impractical to measure in practice, and preserve the general structure of Einstein's theory. They're needed for the quantum consistency, and they're generated by the theory. So you get not literally general relativity, but you get a theory that looks like general relativity where general relativity is accessible, and it preserves the general structure of Einstein's theory. So that was the first set of consequences of replacing the Feynman diagram by a string picture. But there are many other consequences. I think I'll just mention 2 more, or 3 more, sorry. So the first one is that there are far fewer theories than in standard quantum field theory. So in standard quantum field theory, you decide what the particles will be and then what the interactions will be. In string theory, you only get to decide what the string is. And that's subject to very delicate consistency conditions that actually look impossible at first, but very delicately they're obeyed. And when one learns how to do it, one finds that there are 5 ways to do it as counted in the mid-'80s, but only one is understood today. Another thing that happens to you is that the theory picks the space-time dimension. So Feynman took from experiment the fact that he wanted a 4-dimensional theory. We see 3 dimensions of space, but since Einstein, we also count time. But a theory like Feynman's could have been developed in a different dimension. It works better in some dimensions than others. Going up in dimension causes trouble, going down makes it easier. But different dimensions are imaginable. Instead, in string theory, the space-time dimension is picked. And I'll get to that more in a second, but I'll just say, as a teaser, that the answer didn't turn out to be anything that anybody wanted going in. And a third fact is that the theory picks its own symmetries. We don't pick them. Once we get going one of these 5 string theories, or only one is later understood, what the symmetries are going to be is out of our hands. We have to calculate well enough to determine them. Well, the space-time dimension turned out to be 10, which nobody wanted going in. In fact, at first it probably sounded like a joke, although again, this is a joke that played out before I was in the field. So I'm not describing that firsthand. But the joke turned out to be a blessing in disguise. When the theory was reinterpreted as a candidate unified theory of all particles, the extra dimensions gave room to derive the complexity of the real world from a simple starting point. You see, a violin string has higher harmonics. They're labeled by a single integer. The number of half wavelengths that fit between the 2 ends of the string. That's interesting, but the real world of elementary particles is way more complicated. Electrons, muons, neutrinos of 3 kinds, tau particles, many different flavors of quarks, W bosons, and photons, and so on. To get the real world of elementary particles by the vibrations of a string is actually only possible because the extra dimensions give room for more complicated forms of vibration of the string. So, I mean, nobody ever sat down in an ivory tower and said, we're going to solve the problems of field theory by introducing strings, and we'll have extra dimensions which will give us room to get the complexity of the real world. It just was forced upon people who didn't anticipate where they were going in the context of trying to make sense of the trail that was started with the Veneziano amplitude. Well, as for the symmetries, in elucidating them, first of all, physicists rediscovered general covariance and gauge symmetry. General covariance is the fundamental concept in Einstein's theory of gravity. And gauge symmetry is the bread and butter of the standard model of conventional particle physics. So these are symmetries that were already known, although gauge symmetry in the sense of non-abelian gauge symmetry was a comparatively new concept at the time. But in elucidating the symmetries, physicists also discovered a new type of symmetry, supersymmetry. So supersymmetry is the main contribution that string theory has made to predicting something new or generating something new that might be discovered in particle physics. There's at least a decent hope that we might discover supersymmetry at the Large Hadron Collider, the new accelerator that has started working at the CERN laboratory near Geneva rather recently. There are more exotic possibilities, large extra dimensions and the like, where large means large compared to what string theorists usually assume, but actually small compared to the nuclear scale. But at least, I would say, the most compelling suggestion emerging from string theory for something new that might be found at accelerators is supersymmetry. Now, if supersymmetry is right, then regardless of what you think about string theory, it's got to be combined with gravity. And that led to the extraordinarily rich subject of supergravity, which is what we get in making a supersymmetric theory that describes gravity. So supergravity is a kind of partial completion of Einstein's general relativity to include quantum variables in the structure of space and time. Supersymmetry is more or less the same thing for special relativity. So in developing special relativity and general relativity, Einstein assumed that space and time was measured by numbers. It's 3 o'clock, we're at 40 degrees north latitude, 200 meters above sea level, and so on. After Einstein's work, quantum theory was developed, and quantum variables became imaginable, but they were not incorporated previously in the structure of space and time. Supersymmetry and supergravity begin the process of incorporating quantum variables into the structure of space and time, and supersymmetry is the part of that that we might conceivably be able to explore directly experimentally. Supersymmetry and supergravity are actually the tip of a much bigger iceberg. String theory, which has supergravity as a sort of semi-classical limit, is somehow based on a new kind of geometry that we don't understand. So somehow this is a new kind of geometry that turns this kind of Feynman diagram into this kind. And what that is, we certainly don't know. We don't even have a conceptual world in which it's a sensible question. The question has kind of forced itself upon us without our having, even in hindsight, the ability to understand what it really means. That's why it was wisely said in the 70s, not originally by me, that string theory was part of 21st century physics that fell by chance into the 20th century. No one had the conception for it, and to a large extent we still don't today. Somehow there is a new kind of geometry in which you aren't allowed to talk about points or lines in space-time, but you're allowed to talk about quantum minimal surfaces, namely world sheets of a string, except you have to treat them quantum mechanically. But no one at the start foresaw anything like that, and we're still having trouble understanding it. So again, this is part of what I mean in saying that the theory has kept imposing its will upon us. Now, these questions were there in more or less the form I've stated them by the early 80s, but they weren't very popular questions. In fact, living through the period at the time, I was a bit puzzled at how neglected they were. I was, by the early 80s, familiar with the work that was being done by just a few physicists, Green, Schwartz, and Lars Brink, and not many other people, in trying to keep string theory alive or revive it and develop it. But there was puzzlingly little interest until 1984, when a new method of anomaly cancellation found by Green and Schwartz, and a new form of string theory found by Gross, Harvey, Martinek, and Rome, made it possible to derive from string theory a decent rough draft of the real world, with the gauge forces and the quarks and leptons plus quantum gravity. So before 1984, the question existed. There was this new kind of theory based on a new kind of geometry we didn't understand. It made quantum gravity inevitable rather than impossible. It forced us to unify quantum gravity with the other forces, but the details of the elementary particles looked wrong. Most strikingly, there was a problem in incorporating the parity violation that's seen in weak interactions. In 1984, there was a dramatic new theoretical insight, and suddenly the models of particle physics that you could derive interacting with quantum gravity via string theory became vastly more realistic. So to me, that was a sort of signal from heaven. A lot of miracles had gone into string theory up to this point. I've tried to convey this in the first part of my talk, but I think it's been hard to do justice to it. I've only given you a few hints. While a lot of miracles had already happened, and probably many of them were as striking as the anomaly cancellation in their own way and at their own time, this was the first one that really happened while I was watching closely. So it had a big impact on me. And from this point on, string theory and related matters have been my main scientific interest. I'd say in the few years before 1984, string theory and related interests, just in the last few years before 84, were maybe a third of my time or something like that. But after the anomaly cancellation was discovered, it's been my main interest. Now, the prevailing view at the time was that string theory differs from pre-20th century physics because of the role of two parameters. One of them is Planck's constant h bar, and the other one is usually called alpha prime. Now, every physicist knows about h bar. That doesn't depend on string theory. Alpha prime is what's new in string theory. In string theory, alpha prime is a fundamental unit of length, below which ordinary ideas in geometry fail. So the concept of a space-time event makes sense if you don't look too closely, but if you look within a precision of alpha prime, you get trouble. Just like the concept of a point in classical phase space makes sense if you don't look too closely, but if you look within an area h bar, you get into trouble. So alpha prime more or less does to space-time what h bar does to classical phase space. So if string theory is right, the two kinds of deformations are equally important and significant, although they're very different. And most string theorists, and for most part this includes me, spent the decade after 84 studying the alpha prime deformation. The main tool was two-dimensional conformal field theory, which describes propagation of the string. The world history of a string, that tube that I had about 15 minutes ago, when I was comparing the Feynman diagram to the string diagram, it's a two-dimensional surface that's described by two-dimensional conformal field theory. It seemed like our main tool for studying the alpha prime deformation. So typical results of this period were that you could make sense of processes which in conventional geometry you can't describe. I've drawn a picture, but I won't have time to explain it. That's meant to kind of symbolize the idea of a jump in the structure of space-time, which you can't talk about in classical general relativity, but you can talk about when you replace general relativity by string theory. So we had fun in that period discussing stuff like that. The prevailing paradigm was that string theory is based on a new kind of classical theory, an alpha prime deformed theory, that's then supposed to be quantized more or less according to textbook recipes for quantizing classical theories. In other words, the picture is that the classical theory is unusual, but it gets quantized in a normal way. And as I think I told you a moment ago, two-dimensional conformal field theory was seen as the best tool for studying this situation. So it seemed like the important branch of quantum field theory for string theorists. I remember this frustrated me a bit. I'd spent my formative years learning about more general varieties of quantum field theory. In fact, the most basic case is the four-dimensional case that describes ordinary particle physics. And suddenly, instead, it seemed that we were supposed to study another special case, wasting a lot of painfully acquired wisdom. But I don't think I ever channeled this frustration into trying to improve on the then prevailing paradigm. A few physicists, and incidentally a lot of this work was done by British physicists, both here and physicists out of the country, especially Paul Townsend and Mike Duff, among others. But a few physicists did try to go beyond the prevailing paradigm. They started with a simple question: why stop at strings, why not membranes? So I've suppressed time here. This is meant to be a point particle. Here's a string. Here I drew an open string stretched between two quarks. And I'm not a good artist, so this isn't a very good picture of a membrane. But we're trying to imagine that after going from point particles to strings, we should then try membranes. So this question was asked. And if you take the question literally, it actually has a good answer. So strings work better in a certain sense than membranes or other objects because of the unique properties of complex numbers. So a complex number is made from two real numbers, and there's no way to combine any other number of real numbers to get anything with the magical properties of complex numbers. It's true that there are quaternions, and you can do some stuff with quaternions, but complex numbers are special. And in a sense, if you interpret the question literally, that's the answer. but it didn't prove to be the whole story. Eventually, a more subtle version of the membrane idea emerged, and now we know that the membranes in higher objects are actually part of string theory, not an alternative theory, but part of the same theory. Meanwhile, there was another idea developing that also challenged, eventually, the established paradigm. That was electric-magnetic duality. Since the 19th century, physicists had been fascinated by the symmetry of Maxwell's equations in vacuum between electric and magnetic fields. Now, in a sense, it seemed like an accident because, for one thing, in nature we see electric charges and no magnetic ones. And worse than that, quantum mechanics seems to tell us that it's impossible to have a symmetry between electricity and magnetism. Because to write a Schrodinger equation, we need to introduce a vector potential, and the vector potential breaks the symmetry, since we derive the magnetic field from a vector potential and the electric field from a scalar potential. So, okay, the symmetry seemed impossible. But way, way back, Dirac showed that it's actually imaginable to have magnetic monopoles in quantum mechanics. But if you want to do it, you need Dirac's formula for quantization of magnetic charge, which says that the product of electric and magnetic charge of any two objects is an integer in fundamental units that involve Planck's constant. But Dirac did not have a convincing theory that used this idea, and such a theory didn't actually develop until the 70s. Again, in the 70s, as I actually told you before, the modern theory of strong interactions emerged, and it raised a lot of intractable problems, of which the most obvious is that the strong interaction, say a proton, is made of quarks, but we never actually managed to observe an individual quark. The quarks are confined or trapped into objects such as protons. So it was suggested by many of the leading physicists of the time that this could be explained in an alternative version of QCD using magnetic variables. It sounds good, but none of these individuals taught us how to do it. No one knew what the magnetic variables would be in the case of QCD, and all of the people who made this suggestion went on then to work on other things, leaving the rest of us to puzzle over it. There wasn't any real progress until the mid-90s, when progress came in connection with the things I'm telling you about, really, with supersymmetry and string theory. And even today, we only have a partial understanding. The first relatively clear conjecture about how a non-abelian gauge theory, like we use for elementary particle physics, could have symmetry between electricity and magnetism started to emerge in the 70s and emerged in a series of steps. But it took a long time until these ideas were developed in a way that most physicists found convincing and useful. That didn't really happen until the mid-90s. But by the 90s, a number of clues were suggesting that electric-magnetic duality, in other words, symmetry between electricity and magnetism, is important in the general structure of string theory. There were a lot of clues for this, but the most direct one is that such duality was known to be important in the structure of supergravity, which, as I've told you, is a kind of semi-classical limit of string theory. Finally, in the mid-90s, some of the strands I've mentioned, such as membranes and electric-magnetic symmetry, and others that I don't really have time for, were knitted together into a new and more comprehensive viewpoint. All I'll really be able to do today is to give a few hints about the new viewpoint that emerged. First of all, if a symmetry between electric and magnetic charge is important in the structure of a theory, then that means, because there's an h-bar in Dirac's formula, that the basic structure of the theory can only be understood quantum mechanically. So we have to give up on the idea of understanding string theory as a classical theory which then gets quantized. The idea of first understanding the alpha prime deformation and then the h-bar deformation can't be correct. We have to treat them together. That means that in some sense, we're not just quantizing a classical theory. In some sense, if the theory is correct, it must give a new interpretation of what quantum mechanics means. when we do treat alpha prime and h bar together, we get a nice surprise. Instead of the 5 string theories of the 80s, it turns out that there's only one string theory, that is, only one candidate for superunification of the laws of nature. So this can be neatly summarized in this picture, which is oversimplified but still gives you a nice hint. It's a two-dimensional picture where, loosely speaking, the two parameters are the two deformation parameters, h bar and alpha prime. But which is which depends on your viewpoint. There's one theory which has 6 interesting limits. 5 of the limits are the 5 traditional string theories. And the 6th limit is the favorite theory of the supergravity practitioners, which is 11-dimensional supergravity. This funny thing is an acronym for supergravity. And the overarching theory has 5 different limits, plus sort of a 6th. 5 different limits that can be interpreted as classical limits of one kind or another, based on looking at a different parameter and calling it h bar. As for what the overarching theory is that has all these limits, well, you can call it M theory, as I've done and others have done, but that's just to give a name to the unknown. It's better, perhaps, to indicate the overarching theory by a series of question marks. So if you try to think of a two-step process where you first find a new theory and then quantize, then there are 5 string theories. They don't seem to be related to 11-dimensional supergravity. But if you treat alpha prime and h bar together, you discover that there's only one string theory, which is the candidate for superunification of the laws of nature, that has all 5 semi-classical limits plus another one. So the previous paradigm was that string theory is based on 2-dimensional conformal field theory. The new paradigm, the new view, is that all quantum field theory in all dimensions, everything Feynman did or didn't do, and might have done using any variant of his ideas, is grist for the mill, is part of the input for string theory. So, for example, UN is a gauge group similar to what's used in the standard model, except the standard model uses particular values of n. UN for any n in any dimension describes the behavior of n parallel branes, where if you want to know what a brane is, the name was coined by starting with the word membrane, and then in going to an arbitrary number of dimensions, people dropped the first syllable and just kept the syllable brain. So UN gauge theory in any dimension describes the behavior of branes in string theory in a particular situation. So that's an example of what I said here, that everything quantum field theorists do or don't do, or might do, using their methods, have thought of or haven't thought of, in the current view, is part of the grist for the string theory mill. So the reinterpretation of, I should say, the unification of the different string theories in a more comprehensive picture that uses not just 2-dimensional conformal field theory, but all conformal field theory, has got all kinds of applications. I'm going to just mention 2 of them. And the 2 I've picked because they involve areas where string theory is applied to better understand aspects of more conventional physical theories. The reason I want to stress this is that the reason I believe that string theory is on the right track is not only that it solves the problem of quantum gravity and gives a strikingly elegant way to unify quantum gravity with something a lot like the real world of particle physics, or that it's generated a lot of new ideas in geometry that have often startled the mathematicians. But it's also that string theory has often had success in shedding light on not well understood questions that arise in better established physical theories. I don't think that would be happening by chance, and I think it means that the string theory does involve a deeper level of understanding of the conventional physical theories, which enables it to generate insights of which I'll give just very briefly a couple examples. Well, I will really not even be giving you examples. I'll just be describing the strategy behind the examples. The strategy is the following thought experiment. If you want to understand the black holes, you imagine building a black holes out of branes. In Einstein's theory, black holes can be made out of tables and chairs or anything else you want to make them out of. But if you make a black hole by a collapsing cloud of tables and chairs, you have a little bit of trouble in understanding it microscopically. You make a black hole out of something which is simpler, which are brains in string theory, and then you know the quantum laws that describe the brains. In fact, it's what I told you here, UN gauge theory. So you get a situation where you understand the black hole quantum mechanically, and you can use that understanding to compute the Bekenstein-Hawking entropy of the black hole by counting quantum states using methods of gauge theory. So Bekenstein and Hawking discovered in the 70s that a black hole must have an entropy. In the rest of physics, the entropy is the logarithm of the number of quantum states. But it traditionally was an unsolved problem to describe the quantum states of a black hole, count them, and show that the Bekenstein-Hawking entropy is the logarithm of the number of states. That's done here using the link between black holes and gauge theory that you get by forming a black hole out of brains. But you can also do this in reverse and understand gauge theory better. You map questions in gauge theory into questions about gravity. You had the UN gauge theory of the brains, but the brains might form a black hole. And although some questions about black holes are mysterious, there are other questions about black holes that you can answer by solving Einstein's equations. So if you take a question about black holes that Einstein actually knew how to answer, or Einstein and others who used his equations, it might map into a question about gauge theory that you have trouble answering. So when you're lucky, instead of using gauge theory to answer questions about black holes, you can use black holes to answer questions about gauge theory. So this has had a lot of successes. The part I've actually contributed to has to do with understanding confinement of quarks in terms of the formation of a horizon of a black hole. But a more recent and perhaps more spectacular success, I actually mentioned it near the beginning of the talk, has been the modeling of the quark gluon plasma produced at RHIC in terms of string theory and black holes. RHIC is the relativistic heavy ion collider on Long Island. So in sum, in the 1990s, the prevailing view of what string theory means and how one has to try to understand it and what it can be applied to was greatly enlarged again. And it would be fun to be able to tell you a little bit more about that. But I want to try to look forward, or at least more recently, and to ask, what's next? What might be the next major change in perspective? Well, it's famously hard to make predictions, especially about the future. That's actually a remark that's attributed, at least in my country, to a famous baseball player. But I realize that both the individual and possibly the remark might be less famous in this country than in my country. Certainly the sport is less familiar here, although you've got your own local variant in the form of cricket. But this is a case where we have a little bit of trouble, not just in foreseeing the future, but in interpreting the recent past. There has possibly already been another major change in perspective since the period I just told you about, but it's hard to know for sure. You kind of heard about this a year ago from a different point of view in the lecture of the last Newton medalist, Alan Guth. Since there's only one string theory, it seems reasonable to hope that it might have only one quantum vacuum describing our universe and leading to definite predictions for the values of all the dimensionless natural constants, like, for example, the ratio of the mass of the electron to its heavier cousin, the muon. But research in string theory has actually never supported this hope. For example, back in the mid-1980s, models of string compactification to 4 dimensions gave not one possibility, but many that were at least roughly compatible with what we observe. So as I told you, the anomaly cancellation, the generalized anomaly cancellation found in 1984, rather abruptly made it possible in a strikingly beautiful and elegant way to derive from string theory, in other words, from a unified theory of gravity and quantum theory, a unified theory of gravity and something that was at least a good rough draft of the world of elementary particles. But the way of doing this wasn't unique. There were many closely related constructions that were possible. I always hoped that this would go away, but later research always had the effect of generating more possibilities. So I was one of the people working on these constructions, and I'm tempted to say that the proliferation of possibilities was the embarrassment of my youth. Meanwhile, developments in astronomy have made some of our most distinguished colleagues suggest that the real world might be based on just such a megaverse of possibilities. So one who's discussed this a lot is Martin Rees, the Astronomer Royal in this country. It would be hopeless to try to explain all the contributions and all the distinguished people who have made them, but certainly Alan Guth is one who's explored such possibilities, and I think described it in last year's Newton lecture. And his point of view had nothing, well, was not primarily motivated by string theory, was mainly motivated by clues coming from cosmology. The two most relevant developments have been the apparent observation of a tiny but not zero cosmological constant. In other words, the fact that the expansion of the universe is accelerating. That was essentially first observed in around 1998, although it took a couple years for it to be really convincing, at least to me. And the second is the success of Guth's theory of cosmic inflation in describing the fluctuations of the cosmic microwave radiation, the way that when we look at different directions in the sky, we see slightly different temperatures. So the value of the cosmological constant makes the real world look like it actually might be unstable and might be a little bit of an accident. And if the world were described by a megaverse of possibilities, cosmic inflation gives a beautiful way of populating all of the megaverse of possibilities, just starting with one, just starting with something simple. So these clues and others have made some of our colleagues suspect that something like the multiplicity of string theory possibilities might be the way the real world is. But if it's true, we need more clues to make it convincing. If the idea would be that the landscape of string theory vacua, again, I'm not much of an artist. I've tried to draw a mountain range with many valleys. The idea would be that the early universe had many places it could have settled into, and different regions of the universe might have settled into different valleys. The inflationary universe of Alan Guth actually gives away that just starting with one, you'd end up tunneling to all the others. If the landscape of string vacua is the right concept, it's another big shift in our interpretation of the theory. But to my thinking, we still need more clues to have a better picture of whether that is the right interpretation. At any rate, the process of learning what string theory means has a long way still to go. One of the reasons that it is, I think, an exciting topic for today's students to work on is precisely that so much isn't understood. It's sometimes framed as a criticism that string theorists don't really understand their theory. That's true, but if we understood it, it might be finished. The fact that so little is understood and that such relatively small pieces are actually such big discoveries in their own right is part of what makes it exciting. And there's a lot still more to do. Thank you very much.
On behalf of the Institute of Physics, it gives me great pleasure to present the Isaac Newton Medal, the Institute's International Medal, to Professor Edward Witten for your insight, your creativity, your mathematical powers, which have led to numerous and profound transforming contributions in areas of particle theory, quantum field theory, and general relativity. Our many congratulations to you.
Thank you so much, Jocelyn.